In this video, I will be discussing about integrating factors in differential equations. So, when you solve a differential equation, which is not a separable differential equation, not a homogeneous differential equation, and not an exact differential equation, then determining its integrating factor is a way of solving this non-exact differential equation. So given the first order differential equation, which is m of x and y dx plus n of x and y dy, which is equal to 0, and if the partial derivative of this m with respect to y is not equal to the partial derivative of this n with respect to x, then we can say that this differential equation is not an exact differential equation because it does not satisfy the test for exactness. And we know that the test for exactness states that when the partial derivative of this m with respect to y is equal to the partial derivative of this n with respect to x, then this differential equation is an exact differential equation. However, this non-exact differential equation can be made exact by multiplying by a certain suitable function phi called the integrating factor, which I abbreviated here as IF. Now in symbols, if this m of x and y dx, which I write here m dx, so that I can simplify this statement here, and this n of x and y dy, I write here n dy, which is equal to 0, is multiplied by this function phi, then each term will be multiplied by the phi function. So phi times m dx plus phi times n dy equals phi times 0, which is 0. And this resulting differential equation is now an exact differential equation, which means that when you take the partial derivative of this multiplier of dx with respect to y and the partial derivative of n with respect to x are equal, then this given differential equation where we multiplied the function phi is now an exact differential equation. So what we did here is we just multiplied the differential equation by that integrating factor phi, so that this differential equation can be converted to an exact differential equation. So our goal this time is how to find this integrating factor phi for a given differential equation. Now, looking at this equation, we can solve for the partial derivative of this product phi and m with respect to y. So, applying the product rule, we have phi times the partial derivative of m with respect to y plus m times the partial derivative of phi with respect to y. And this is the derivative for this product phi and m. Also, we need to find the partial derivative of this product phi and n. So, this is equal to phi times the partial derivative of n with respect to x plus n times the partial derivative of phi with respect to x. So to solve for our integrating factor phi, we need to group all the terms having phi at the left and all the terms without phi at the right. So we have the phi times the partial derivative of m with respect to y minus this phi times the partial derivative of n with respect to x is equal to n times the partial derivative of phi with respect to x minus this one. So we have m times the partial derivative of phi with respect to y. So factoring the common factor, which is phi, we have phi times the partial derivative of m with respect to y minus the partial derivative of n with respect to x is equal to n times the partial derivative of phi with respect to x minus m times the partial derivative of phi with respect to y. And because this is very scary to see, we will replace that symbol by a symbol that is very, very light for us. So this partial derivative of m with respect to y can be replaced by just simply m sub y or just my. And this partial derivative of n with respect to x, we just replace that one by n sub x or simply next. So we can write this equation as phi times the m sub y minus n sub x, which means that this is the partial derivative of m with respect to y minus the partial derivative of n with respect to x, which is equal to n times the partial derivative of phi with respect to x minus m times the partial derivative of phi with respect to y. So allow me to label this equation as equation 1 and this equation as my equation 2 here. And there are three cases that could happen here. And the first case could happen if our integrating factor is a function of x alone. Then this equation number 2 reduces to the equation phi times the partial derivative of m with respect to y minus the partial derivative of n with respect to x, which is equal to our n times the derivative of phi with respect to x. And this is because our partial derivative of phi with respect to y is 0. Why? Because phi is a function of x alone. So if this is in terms of x alone, then its partial derivative with respect to y is 0 because we treat our x's as constants here. So the derivative of our function of x with respect to y is 0. And also, we have that the partial derivative of phi with respect to x is the same as the derivative of phi with respect to x. So we are now writing this one as the standard derivative, not in partial derivative. Why? Because phi is in terms of x alone. So if this is in terms of x's, then its partial derivative with respect to x is the same as the derivative of this x's with respect to x. So multiplying by dx over n times the phi, we have the partial derivative of m with respect to y minus the partial derivative of n with respect to x divided by n times dx, which is equal to the derivative of phi over phi. Because when you multiply this one to both sides of the equation, this phi and this phi cancels. But this dx over n will be multiplied here. And the result is this one here. But at the right hand side of the equation, this n and this n cancels each other, and also dx with this dx cancels each other. So what remains is the derivative of phi over phi here. And you notice that this is already a separable differential equation. Now, suppose this partial derivative of m with respect to y minus partial derivative of n with respect to x over our n is only a function of x alone, then this expression can be replaced by f of x times dx, which is equal to the derivative of phi over phi is a separable differential equation. So if we take the integral of both sides of this equation, we have the integral of f of x dx, which is equal to the natural log of phi function, because we know that the integral of the differential of phi over phi is the natural log of phi. Now, if we will raise these both sides of the equation to e, so we have e raised to the exponent of the integral of f of x dx, which is equal to e to the exponent of the natural log of phi. From here, this e to the power the natural log of phi is just equal to phi. So phi is equal to e to the power of the integral of f of x dx. And this is now our integrating factor when the result of this expression is purely a function of x alone. But if your phi function is a function of y alone, then this equation 2 reduces to phi times the partial derivative of m with respect to y minus the partial derivative of n with respect to x is equal to minus m times the derivative of phi with respect to y. Since our partial derivative of phi with respect to x is 0. Why? Because if your phi function is in terms of y alone, then taking its partial derivative with respect to x is 0, because the y's here in this phi are treated like constants, and we know that the derivative of a constant is 0. And also, our partial derivative of our phi with respect to y is the same as the derivative of our phi with respect to y. So here we change the partial to the standard derivative notation. Why? There is no need for you to take the partial derivative of phi with respect to y, because our phi is in terms of y alone. So multiplying both sides of the equation by dy over negative m times the phi function, we have this partial derivative of m with respect to y minus this partial derivative of n with respect to x, when divided by minus m times dy is equal to the differential of phi over our phi function. And this happens because this phi here and this phi here cancels each other. So this dy over negative m will be the multiplier of this binomial here. So we have this one here. But this negative m and this negative m cancels each other, together with this dy, and this dy here also cancels each other. So what remains is the differential of phi over phi here. And we notice that this is already a separable differential equation. So if we replace this partial derivative of m with respect to y minus this partial derivative of n with respect to x over m by g of y, because if this is in terms of y alone, then instead of writing this one, we will replace this expression by g of y. But there is a negative here, so we will write the negative of the g of y times dy, which is equal to the differential of the phi function over phi. And because the variables are now separated, we can take the integral of both sides of the equation. So we have the negative of the integral of the g of y dy is equal to the natural log of phi, because we know that the integral of the differential of phi over phi is the natural log of phi. And then raising these two expressions to e, we have e to the power of the negative of the integral of g of y dy is equal to e to the power of the natural log of phi. And we know that e to the power natural log of phi is just phi, because this e and the natural log cancels each other. So we have phi, which is equal to this e to the exponent of negative of the integral of g of y dy. And this is our integrating factor when this expression is in terms of y alone. But if the phi function is not in terms of x alone or not in terms of y alone, but it's a product of some powers of x and some powers of y, then taking the partial derivative of this phi here with respect to x is equal to m x to the power m minus 1 using the power rule for x to the power m. But this y to the power n will be copied because this is treated like constant. And also taking the partial derivative of our phi with respect to y, we have n times x to the power m times y to the power of n minus 1, because x to the power m is treated like constant when finding the partial derivative with respect to y. So applying the rule for the power, we have n times y to the power n minus 1. And substituting this one to equation 2, we have our phi, which is this one, which is x to the power m and y to the power n times the partial derivative of m with respect to y minus the partial derivative of n with respect to x is equal to this n times the partial derivative of phi with respect to x, which is this one here. So this is n times m times x to the power m minus 1 times y to the power n. And this will be subtracted by m times the partial derivative of phi with respect to y, which is this one here. So we have times n x to the power of m times y to the power of n minus 1. And dividing both sides of the equation by x to the power m times y to the power n, we have the partial derivative of m with respect to y minus the partial derivative of n with respect to x is equal to the quotient of our n times m times x to the power m minus 1 times y to the power n minus m times small n times x to the power m times y to the power of n minus 1. And this will be divided by x to the power m, y to the power n. Now dividing these two terms here by this product x to the power m by y to the power n, we have the partial derivative of m with respect to y minus the partial derivative of n with respect to x is equal to big N times m over x, because our y to the power n and also this one cancels here, and this x to the power m minus 1 and x to the power m will give you x in the denominator minus the big N times small n all over y, because this x to the power m and this x to the power m here cancels each other. So this y to the power n minus 1 divided by y to the power n is y in the denominator. And this resulting equation gives no assurance of yielding the values of the exponents of m and n in this integrating factor phi. However, if the terms at the left side of the equation are similar to the terms at the right side of this equation, then it is possible to determine the values of m and n here, which are the exponents in our integrating factor. In other words, that for the equation here to give the values of m and n, then it must possess the properties of an identity equation. And when the values of the small m and small n here, which are the exponents of our integrating factor, can be solved, then our integrating factor is determined here, which is phi, which is equal to x to the power m times y to the power n. And these are the three cases that can happen in this resulting equation. So at this point, let us summarize the three cases here. So let this m sub y as the partial derivative of m with respect to y, and this n sub x as the partial derivative of n with respect to x. Then the case 1 states that your partial derivative of m with respect to y minus the partial derivative of n with respect to x when divided by n, and the result is a function of x alone, then our integrating factor is e raised to the exponent to the integral of your f of x, which is this one. And this resulting expression is our integrating factor. But when this expression is a function of y alone, then our integrating factor is obtained by e raised to the exponent of the negative of this integral g of y dy. And this is our integrating factor when this results to a function of y alone. But when this expression is not a function of x alone and not a function also of y alone, then our integrating factor is some powers of x times some powers of y, where the exponents of m and n can be determined in this equation here. So to illustrate these three cases, let's take some examples here. So example number 1, find the general solution to this differential equation. And if this will come out in the exam, you will not be told what kind of differential equation is this. So you may check whether this is a separable differential equation. And you can notice that this is a difference of x and y as multiplier of dx. So therefore, this is not a separable differential equation. And this is not also an exact differential equation. And to prove that, we need to solve the test for exactness, which is the partial derivative of m with respect to y. And we know that our m here is the multiplier of the dx. So we have 8xy here. And we have also minus 9y squared. And we take the partial derivative of this with respect to y. And taking this partial derivative, we have 8x, because 8x is treated like constant here. So the partial derivative of 8xy with respect to y is 8x, and the partial derivative of 9y squared with respect to y is 18y. And also, we need to find the partial derivative of n with respect to x. And we know that our n is the multiplier of dy. So we have 2x squared and we have minus 6xy. So taking the partial derivative with respect to x, we have this 4x, because the partial derivative of 2x squared with respect to x is 4x using the power rule. And this minus 6y in this term is treated like constant. So the partial derivative of this is negative 6y. And you can see that the partial derivative of m with respect to y is not equal to the partial derivative of n with respect to x. So therefore, we say that this dE is non-exact differential equation. And since this is a non-exact differential equation, we will make it an exact differential equation by applying this method here. So let's try case 1, wherein we need to find the partial derivative of m with respect to y minus the partial derivative of n with respect to x divided by n. And substituting the values for this, we have this partial derivative of m with respect to y, which is this one here. So substituting that one, 8x minus 18y, we need to subtract this one by the partial derivative of n with respect to x, which is this one also. So we have to subtract 4x minus 6y. And this will be divided by n. And our n is this one here. So we have 2x squared minus 6xy. So simplifying this one, we have 8x minus 4x. We have 4x here. And minus 18y plus 6y, we have minus 12y. Because the minus of the minus, the result is plus. So minus 18y plus 6y is negative 12y. And this will be divided by 2x squared minus 6xy. And if we're going to simplify this one by factoring the common term in these two terms, we have 4 times x minus 3y. And this will be divided by 2x times x minus 3y. And you can check that when you multiply 2x by x, we have this one here. And if you multiply 2x by minus 3y, we have negative 6xy. So therefore, we can cancel these two factors. So what will remain is 2 over x, because we can also cancel the 2 in this 4 here and the 2 here in the denominator. So we have 2 over x, which is a function of x alone. So we have the result of our partial derivative of m with respect to y minus the partial derivative of n with respect to x divided by n is a function of x alone. Therefore, we will use this case number 1 to determine our integrating factor. So, using case number 1, we can determine our integrating factor, which is equal to e to the power of the integral of this function 2 over x dx here. And factoring out this constant 2 outside the integral symbol, we have phi, which is equal to e to the power of 2 times the integral of dx over x. And we know that the integral of dx over x is ln x. And applying the properties of the logarithm, we have ln of x squared here, because these two can be an exponent of x. And we know that e to the power the natural log of x squared is simply x squared. So our integrating factor is x squared. So this is now our phi function. So multiplying all terms in the differential equation by this integrating factor x squared, we have x squared times y times 8x minus 9y dx. And this will be added to x squared times 2x times x minus 3y times dy, which is equal to 0. And multiplying this term to this binomial here, we have 8x cubed times y minus 9x squared y squared, and this is multiplied by dx, plus 2x to the power 4 here, because x squared times x is x to the power of 4, and this will be subtracted by 6x cubed y. So this is multiplied by dy, which is equal to 0. And you can check that this differential equation is now an exact differential equation. So we write here, this is an exact differential equation. So using the method of solving the exact differential equation, we take the partial integral of your m of x and y partially with respect to x, and the answer is some function which is in terms of x and y plus a function that is in terms of y alone, because this is partial integration with respect to x, so we may expect some function which is in terms of y if there's any. So we have f, which is equal to the partial integral of our m, which is 8x cubed y, so here, and then minus 9x squared y squared partially with respect to x. So we have f, which is the 8y, because 8y is treated like constant here, times the integral of x cubed, which is x to the power 4 over 4. And this will be subtracted by 9y squared, because 9y squared is treated like constant here. and we take the integral of x squared, which is x cubed over 3. And this will be added to some function in terms of y, if there is any, plus the constant of integration c. So our f is equal to 2x to the power of 4 times y minus 3x cubed y squared plus our h of y plus the constant of integration c. And also we can obtain our solution big F when you take the partial integral of our n, which are in terms of x and y, partially with respect to y. And we expect that the answer is some function of x and y plus a function that is in terms of x alone. So our partial integral of n, which is here 2x to the fourth minus 6x cubed y partially with respect to y, is equal to 2x to the fourth y, because 2x to the fourth is treated like constant here, and then we have 6x cubed as constant times y squared over 2, because this is with respect to y, and this will be added to some function which is in terms of x alone plus the constant of integration c. So we have our solution big F, which is equal to 2x to the fourth y minus 3x cubed y squared plus the g of x plus the constant of integration c. And comparing these two solutions here, we have our h of y as 0, because we don't have terms which are in terms of y alone here, and we don't have also terms which are in terms of x alone. So our g of x is also 0. Hence, our solution to the given differential equation is the term that is common to this expression, which is 2x to the fourth y minus 3x cubed y squared, which is equal to the constant of integration c. So this is now our solution to the given differential equation, which is not an exact differential equation, but we made it an exact differential equation by multiplying this integrating factor x squared. However, solving this exact differential equation, which is very tedious here, we can have an alternative solution here. So this is now an alternate solution for this exact differential equation, and we can do that by multiplying this dx to this binomial here. So we have 8x cubed y dx minus 9x squared y squared dx plus 2x to the fourth dy minus 6x cubed y dy, which is equated to 0. And combining the terms which are having higher exponents of x, we have 8x cubed y dx plus 2x to the fourth dy. So we group them as 1, and we subtract here our 6x cubed y dy, which is from here, and we add here plus 9x squared y squared dx, and this is equated to 0. So factoring the common numerical coefficient here, we have 2 times 4x cubed y dx plus x to the power 4 dy, and also this one factoring the common numerical coefficient, which is 3. So we have 2x cubed y dy plus 3x squared y squared dx, and this is equated to 0. And we notice that this one is already an integrable combination because this is the differential of x to the power of 4 times y. And you can check using the product rule that the derivative of x to the power of 4 is 4x cubed times y plus the derivative of y, which is this, times the x to the power of 4. And this will be multiplied by 2. And also we noticed that this is also an integrable combination, which is the differential of x to the power of 3 times y squared. And you can check using the product rule that the differential of this is this one here, that we have x cubed times the derivative of y squared, which is 2y, plus y squared times the derivative of x cubed, which is 3x squared. And this will be multiplied by a constant of 3 here. And the whole expression is equal to 0. And taking the integral to each term of this equation, we have this one minus the integral of 3 times the differential of x cubed y squared, which is equal to the integral of 0. So factoring out the constant here, we have 2 times the integral of the differential of x to the power 4 times y minus 3 times the integral of the differential of x cubed times y squared, which is equal to the integral of 0. But the integral of the differential cancels each other, so we have 2x to the power of 4 times y minus 3 times the integral of the differential, which cancels each other, so we have x cubed times y squared, and this is equal to the constant of integration c. And you can check that this one is the same answer as this one. So this method is using the integrable combination, which is a shorter one compared to this method. Let's proceed to our example number 2. Find the general solution to this differential equation. And you can check that this is also not a separable differential equation. And this is not also a homogeneous differential equation, and not an exact differential equation. And we can show that one, that this is not an exact differential equation by finding the partial derivative of m with respect to y. Because our m, we have this one, 4xy plus y squared minus 2y. And taking the partial derivative of this with respect to y is equal to 4x, because with respect to y, 4x is treated like constant. So the derivative is 4x. And also the derivative of y squared with respect to y is 2y. And the derivative of minus 2y with respect to y is minus 2. Also, taking for the partial derivative of n with respect to x, we have our n, which is xy plus 1. And taking the partial derivative of that with respect to x, we have y. Because y here is treated like constant, and the derivative of 1 is 0. So we have y as our partial derivative of n with respect to x. And since we notice that the partial derivative of n with respect to y is not the same as the partial derivative of n with respect to x, then this differential equation is not an exact differential equation. And because this is not an exact differential equation, we need to convert it to an exact differential equation by trying case number 1. So try case 1 in the non-exact differential equation by solving our partial derivative of m with respect to y minus the partial derivative of n with respect to x divided by n. And we know that our partial derivative of m with respect to y is this one here. So we have 4x plus 2y minus 2 when subtracted by the partial derivative of n with respect to x, which is y, and this is divided by our n, which is xy plus 1. We have the result as 4x plus y minus 2 because 2y minus y is y, and this will be divided by xy plus 1. And since we cannot reduce this one anymore, we notice that the resulting expression is not a function of x alone. So we write here, since this is not a function of x alone, then case number 1 is not possible. So next, we try case number 2, which can be obtained by the partial derivative of m with respect to y minus the partial derivative of n with respect to x divided by m. And we know that our partial derivative of m with respect to y is this one here. So we have 4x plus 2y minus 2, and this will be subtracted by our partial derivative of n with respect to x, which is y, and divided by our m, which is this one, 4xy plus y squared minus 2y. And simplifying our numerator, we have 4x plus y minus 2 because 2y minus y is y. But the denominator can be factored to its common monomial factor, which is y. So we have 4x plus y minus 2. And you see that we can cancel this one here. So we have our resulting expression as 1 over y. Thus, our case number 2 is possible here. So our integrating factor is obtained by raising our e to the exponent of negative of the integral of our function 1 over y. And this is with respect to y. So we have the integrating factor as e to the power of the negative of the integral of dy over y. And we know that the integral of dy over y is the natural log of y. But this negative here can be used as an exponent of y. So we have our integrating factor as e to the power of the natural log of y to the power negative 1. And we know that when e is raised to the exponent of the natural log, the result cancels each other. So we have y to the power negative 1, or simply 1 over y. So this is now our integrating factor for our differential equation. So multiplying 1 over y, we have 1 over y times 4 4x plus y minus 2 times dx plus 1 over y times xy plus 1 dy, which is equal to 0. And multiplying this 1 over y to this y here, we have 4x plus y minus 2 times dx. And when we distribute this 1 over y to this binomial here, we have x plus 1 over y times dy, and the sum is equal to 0. And you can check that this resulting differential equation is now an exact differential equation. So solving this exact differential equation, we need to integrate partially our m, which is in terms of x and y with respect to x, and we expect that the answer is some functions of x and y plus the function of y alone here. And we know that our m, which is equal to this trinomial here, 4x plus y minus 2 with respect to x, is equal to 4 times x squared over 2, because the integral of x is x squared over 2, and the integral of y is yx with respect to x, because y here is treated like a constant, and the integral of negative 2 with respect to x is minus 2x, and this is added to our h of y plus the constant of integration c. So our solution big F is equal to 2x squared plus xy minus 2x plus h of y plus the constant of integration c. And of course, we need to find also our solution big F using our n function, which is in terms of x and y. But this is integrating with respect to y. So we expect that our answer is in terms of x and y plus some function g, which is in terms of x alone here. So we have our solution big F of the partial integral of our n, which is this one here, x plus 1 over y with respect to y is equal to xy plus the integral of dy over y is the natural log of y plus the function, which is in terms of x alone, plus the constant of integration c. So our big F is equal to xy plus the natural log of y plus the g of x plus the constant of integration c. And comparing this expression here with this expression, we say that our h of y is ln of y, because this is the only term here that is in terms of y alone. And for our g of x, we have this 2x squared and minus 2x, because those are the only terms that are in terms of x alone. Hence, our final answer for this differential equation, we have the common, which is this one here, xy, plus our h of y, which is the natural log of y, plus the g of x, which is 2x squared minus 2x, and this is equated to the constant of integration c. So this is now our solution to the given differential equation. But this method of solving this exact differential equation can be shortened if we apply integrable combination. So we may write here an alternate solution for this converted exact differential equation. So, distributing our dx to this trinomial, we have 4x dx plus y dx minus 2 dx plus x dy plus dy over y, which is equal to 0. And you notice that this one and this one forms an integrable combination. So we may group them together as y dx plus x dy as one group. And then we group also this one, which are solely in terms of x. So we have plus 4x minus 2 dx. And we have the last term here, which is dy over y, which is equal to 0. And we notice that this is already an integrable combination because this is a differential of x and y. And this is added to this 4x minus 2 dx plus dy over y, which is equal to 0. So taking the integral to each term in this equation, we have xy because the integral of the differential cancels each other, and this is added to 4 times x squared over 2 minus 2x plus the natural log of y, which is equal to the constant of integration c. And simplifying this one, we have xy plus 2x squared minus 2x plus the natural log of y, which is equal to the constant of integration c. And you can check that this one is just the same answer as we have in the first solution. So let's proceed to our third example here. Find the general solution to this differential equation. And as you can see, that this is not a separable differential equation. And this is also not a homogeneous differential equation. And also, this is not an exact differential equation. Because if you can apply the test for exactness here by taking the partial derivative of m with respect to y, where our m is only 2y here, this one, taking the partial derivative with respect to y is only 2. And the partial derivative also of n with respect to x is taking the partial derivative of our n, which is x minus x cubed y cubed with respect to x. And the partial derivative is 1 here. And this is subtracted by y cubed because y cubed is treated like constant. And this will be multiplied by the derivative of x cubed, which is 3x squared. So our partial derivative of n with respect to x is 1 minus 3x squared y cubed. And since this partial derivative of m with respect to y is not the same as the partial derivative of n with respect to x, then this differential equation is not an exact differential equation. So now, let us try case number 1 by solving for the partial derivative of m with respect to y minus the partial derivative of n with respect to x divided by n. And we know that our partial derivative of m with respect to y is 2 here. And the partial derivative of n with respect to x is this one here. So this is minus 1 minus 3x squared y cubed. But this will be divided by our n here. And our n is this one, which is x minus x cubed times y cubed. So simplifying this one, we have 2 minus 1 is 1, and minus of the minus is plus 3x squared y cubed. And this will be divided by our n, which is x minus x cubed y cubed. And since this one is not a function of x alone, then we say that case number 1 is not possible. So let's try case number 2. So try case number 2 by solving the partial derivative of m with respect to y minus the partial derivative of n with respect to x divided by m. And we know that our m is 2 with respect to y, and the partial derivative of n with respect to x is this 1 minus 3x squared y cubed, but this will be divided by our m, which is 2y. So we have 1 plus 3x squared y cubed, and this will be divided by 2y. And we notice that the resulting expression is not a function of y alone. Then we say that case number 2 is not possible in this differential equation. So let's try case number 3. And according to case number 3, we need to solve for our big M times small n divided by y. And this will be subtracted by big N times small m divided by x, which is equal to the partial derivative of our big N with respect to x minus the partial derivative of m with respect to y. So substituting our m, which is 2y here, we have 2y times n, and this will be divided by y, and minus our big N, which is this one, x minus x cubed times y cubed. So this will be multiplied by small m divided by x, and this will be equal to the partial derivative of n with respect to x, which is this one here. So 1 minus 3x squared y cubed, and this will be subtracted by our partial derivative of m with respect to y, which is 2. So 2y divided by y is 2, and then this will be multiplied by n minus this binomial when divided by x is 1 minus x squared y cubed times m, and this is equal to 1 minus 2, it's minus 1, and this is subtracted by 3x squared y cubed here. So distributing this m to this binomial, we have 2n minus m plus m x squared y cubed, and this is equal to minus 1 minus 3x squared y cubed here. So by comparison, these terms here which don't have any x and y is equal to this term which don't have x and y at the right hand side of this equation. So we say that 2n minus m is equal to the negative 1. And also we say that this coefficient of x squared y cubed is the same as the coefficient of x squared y cubed in the right hand side of this equation. So our m here is also equal to negative 3, by looking at this coefficient and this coefficient here. So substituting our value of m in this first equation, we have 2n minus m, which is minus 3, is equal to negative 1. So 2n plus 3 is equal to the negative 1. So 2n is equal to the negative 1 minus 3. Therefore, n is equal to negative 4 over 2. So n is equal to the negative 2. Now that we have our values of m and n, hence we can determine our integrating factor phi, which is equal to x to the power m times y to the power n. And we know that m is negative 3 and n is also negative 2. So multiplying to each term in the given differential equation by x to the power negative 3 and y negative 2, we have x to the power negative 3, y to the power negative 2 times 2y dx plus x minus x cubed y cubed dy, which is equal to 0. We have 2x to the power negative 3 and y to the power negative 1 dx plus this x when multiplied by x to the power negative 3, we have x to the power negative 2 y to the power negative 2 minus y. So this is multiplied also by dy, which is equal to 0. And you can check that this is already an exact differential equation. So since this is an exact differential equation, we can solve for our solution big F by taking the integral of our m, which is in terms of x and y, partially with respect to x. And we expect an answer which is in terms of x and y plus a function that is in terms of y alone. So we have big F, which is equal to the integral of our m, in which case this is 2x to the power negative 3 y to the power negative 1 with respect to x, and we have 2 times the integral of x to the power negative 3, which is x to the power negative 2 over negative 2. And because y to the power negative 1 is treated like a constant, we just multiplied that 1 and plus h of y as the constant of integration c. So we have our big F, which is the negative of x to the power negative 2 y to the power negative 1 plus h of y plus the constant of integration c. And also we can find our big F by integrating partially our n, which is in terms of x and y, partially with respect to y. And we expect an answer which is in terms of x and y plus a function which is in terms of x alone if there is any. So we have our n, which is this one here, x to the power negative 2 y to the power negative 2 minus y, but this is with respect to y. So we have this x to the power negative 2 as constant, but the integral of y to the power negative 2 is y to the power negative 1 over the negative 1 minus y squared over 2, and this will be added to some function g of x if there's any, plus the constant of integration c. So our f is equal to the negative of x to the power negative 2 y to the power negative 1 minus y squared over 2 plus the g of x plus the constant of integration c. And comparing this expression with this expression here, we recognize that our h of y is this one here, because this is the only term that is in terms of y alone. And our g of x is equal to 0 because there is no term that is in terms of x alone. Hence, our solution is the common term here, which is the negative x to the power negative 2 times y to the power negative 1 plus the h of y, which is y squared over 2, and this is equated to the constant of integration c. And simplifying this expression here, we have negative of 1 over x squared y minus y squared over 2, which is equal to c. And multiplying both sides of the equation by this minus 2x squared y, we have positive. So this is positive 2 plus this negative times negative is also positive x squared y cubed, which is equal to the constant of integration c x squared y, because this constant negative 2 times the constant c, the product is still a constant. So this is now our solution for the given differential equation. But this solution can be shortened if we can recognize integrable combination for this differential equation. So we can offer an alternate solution here by distributing this dy to this binomial. So we have 2x to the power negative 3 y to the power negative 1 dx plus x to the power negative 2 y to the power negative 2 dy minus y dy, which is equal to 0. And by factoring a negative 1 in these two terms here, we have negative of the negative 2 x to the power negative 3 y to the negative 1 dx minus 1 of x to the power negative 2 y to the power negative 2 dy minus y dy, which is equal to 0. And you can recognize that this is already an integrable combination, which is the differential of x to the power negative 2 y to the power negative 1. But there is a negative outside here, and you can check that the derivative of this product is this one here, which is also subtracted by y dy. And taking the integral to each term in this differential equation, we have this negative of x to the power negative 2 times y to the power negative 1 minus y squared over 2, which is equal to the constant of integration c. And multiplying this one by the negative 2x squared y, we have 2 plus x squared y cubed, and this is equal to cx squared y, because the negative of the negative 2 is positive 2, and this minus 2 cancels with the minus 2 here, so we have 1x squared y cubed. But this negative 2, which is a constant, times this constant c, is still a constant c. So this is now our final answer for the given differential equation. And you can check that this one is the same as our answer using this method for the exact differential equation. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.